We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Get my feet out. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you're listening to episode 114 of the Space Rocket History Podcast. And now, Apollo Command Module Design and Development, 1963 through 64, Part 2. Recall from episode 113, I covered one of the natural phenomena that had the potential to end the Apollo program, and that was micrometeorites. But there was another natural phenomenon that could have stopped Apollo as well. The threat of lingering death from solar radiation. Every once in a while, the sun's surface will erupt with a great flare that boils up across hundreds of thousands of miles, blasting showers of subatomic particles into space at speeds of several hundred miles a second. On Earth, we can tell when one of these radiation showers is on the way because it fills the polar skies with curtains of light, the aurora. As the particles spiral down through the Earth's magnetic field, fortunately, the atmosphere deflects and absorbs most of the radiation. Otherwise, any attempt at life on Earth would have long since been fried out of existence. But for the 3 voyagers on their way to the moon, there would be no place to hide. Once again, nobody knew the full scope of the danger. But what little NASA planners did know was unsettling. The astronomers told them they couldn't have picked a worse time to leave for the moon. People had been charting sunspots since the 17th century and had established that solar activity, for some reason, follows an 11-year cycle. The next peak of solar activity would be in 1968, right in the middle of the Apollo launch schedule. At North American Aviation, Bud Benner, one of the assistant chief engineers, asked Marty Kinsler and a couple of the thermodynamics people to come up with a roundhouse estimate to see what they were up against. He told them to use the highest predicted solar flare models and figure out how much of the radiation would be blocked by the spacecraft structure. A couple of weeks later, the calculations came back, and it looked like they were going to have to supply a water jacket for each crewman with at least 3,000 pounds of water to protect them from the solar radiation. That was a worst-case scenario. Kinsler and his people took another crack at the calculation, this time not assuming a worst-case scenario. Meanwhile, NASA's relentless critic, Jeremy Wisner, the president's science advisor, used the specter of the solar flare to browbeat NASA because it was one area where the agency didn't have a ready answer. But, as it turned out, Wisner could have saved his breath once again. In the final design of the command module, the walls were so jam-packed with transmitters, pumps, and gyros that the astronauts were virtually sealed in a shielded cocoon of hardware. They were probably safer than the average airline passenger. So, solar radiation would not stop Apollo. Which brings us to the issue of component reliability and astronaut safety. From very early in design, a concept had developed that the astronauts would repair or replace a malfunctioning part in the spacecraft during flight. This would, of course, require tools and spare parts to be carried on the missions, which would create a weight problem. Was there a better way of accomplishing this? And just how reliable did the components in the spacecraft have to be? For some time, Gilruth and Max Faget had been struggling with these issues. Faget's position was that, considering the difficulty of the job, if each mission was successful half the time, it would be well worth the effort. But Gilruth thought that was too low. He wanted a 90% mission success rate and a 99% astronaut safety rating. Walt Williams, who was currently running the Mercury program, believed that astronaut safety needed to be only one failure in a million. Gilruth considered that figure unrealistic. Eventually they came up with the figure of 99.9% for crew safety, which meant one catastrophic failure in 1,000. This number, which became known as the triple nines, turned out to be the most important single number in the Apollo program. If they had dropped one decimal place, the cost of the program would have been cut in half. If they added one decimal place, there would not have been enough money on the planet to fund the Apollo program. Now, moving on to component reliability. In the airplane business, they had always established the reliability of their components by testing a bunch of them until they fell apart. Once they knew how long a particular item was likely to last, they could schedule a replacement well before it reached old age. But for Apollo, this kind of straightforward approach was out of the question. The components would have to be infinitely more reliable this time because almost any failure could be fatal. There are no emergency landing strips on the way to the moon. And besides, there wasn't enough time to establish such high levels of reliability through destructive testing. They would instead rely on engineering analysis, which is essentially an educated guess based on the design of the part, what it was made of, and what it would be subjected to in real life. Unfortunately, the analytic method of establishing the reliability of components imposed some staggering demands on the manufacturing people. The only way you could infallibly predict the behavior of a given part was to be certain of everything that went into it: its manufacturing heritage, its precise chemical makeup, and that meant tracking the metal all the way back to the mine. The system they worked out was called traceability, and it was rigorously applied to every piece of Apollo and the huge Saturn booster as well. As each part moved through the manufacturing process, it was accompanied by a packet of documents that established its genealogy and the pedigree of every switch and resistor and screw and fastener that went into it. The saying was, quote, "If you order a piece of plywood, they want to know which tree it came from," end quote. In truth, it was worse than that. The dimensions of the problem came to light in an eye-opening incident early in the program. A whistleblower at North American wrote a letter to his congressman charging that the company was mismanaging Apollo and price gouging the government. One piece of evidence he pointed to was a particular half-inch steel bolt used in the command module. The man said he could go to any hardware store in town and pick up a bolt like that for about 59 cents, and North American was paying $8 to $9 a piece for them. Somehow the letter found its way into the hands of Olin Teague, chairman of the House Space Committee, and he immediately called a hearing. Charlie Felts had to drop everything and fly to Washington with a bunch of flip charts and try to calm the lawmakers down. He explained to the committee that there were 11 steps in the manufacture of these bolts, and they had to be certified at each step. Not only had the bolt itself been subject to rigorous testing, but the steel rod it was milled from had been tested, as had the billet from which the rod was extruded and the ingot from which the billet was forged. Indeed, they knew where the iron ore had come from, the Mesabi Range north of Duluth. And they knew which mine and what shaft. And when you factored in all that extra information, it turned out the actual cost of the bolt was not $8 or $9, but more like $32. This concept of accountability pursued each piece of hardware through the manufacturing process and followed it out the door and onto the launch pad. By some estimates, nearly half the effort that went into building Apollo went into testing components. In addition to reliability through manufacturing and traceability, North American was directed in April 1964 to install redundant systems in the command module. So, if something did go wrong, the crew would be able to shift to another system that could perform the same function as the malfunctioning one, instead of carrying parts and tools to make repairs while in space. Late in 1963, Houston started taking measures to increase its control over and improve on subsystem development, chiefly to get the more advanced Block 2 command module underway. Joseph Shea asked Max Faget to pick experts in the engineering shops to act as subsystem managers. The managers were directed to oversee their components from design through manufacture and test. They were responsible for cost, schedule, and reliability. When changes in one unit became necessary, other systems had to be considered and any conflicts resolved before alterations could be made. It turned out that the subsystem manager concept was an excellent measure for restraining engineers who usually wanted to make improvements to hardware that was functioning adequately. Both North American and Grumman, the lunar module manufacturer, also made significant contributions toward controlling hardware development. As far back as mid-1962, John Disher urged Houston to draft hardware development and flight test schedules through the first manned lunar landing. Houston submitted these schedules in October 1962, but when 1963 rolled around, delays had made this paper meaningless. Near the end of that year, North American invited the other two contractors, Grumman and MIT, to help settle this scheduling issue. The contractors drew up charts on all three modules, command, service, and lunar. They included developmental test of subsystems, ground test of partially and fully assembled modules, and Saturn-boosted flight test of completed modules. Their report to NASA outlining the test and exact uses of each piece of hardware for the years 1964 through 1968 was called Project Christmas Present by the contractors. A second move, led by Grumman, was made in the early months of 1964. Grumman officials had complained to Shea that the frequent changes in lunar mission concept made it impossible for the design and development engineers to decide what components they needed. The general outline of the mission was pretty well set, but the haziness about specific refinements was playing havoc with attempts to design hardware to cover all normal and contingency operations. Shea told Grumman to see if they could get the requirements pinned down. North American and MIT crews soon joined the lunar module contractor to team up together and create a design reference mission. First, the group looked at what Apollo was supposed to accomplish, which was to land 2 astronauts and scientific equipment on the near-Earth side surface of the moon and return them safely to Earth. A second major objective was to carry more than 100 kilograms of scientific equipment to be set up on the moon and to bring back more than 30 kilograms of lunar soil and rocks. To make sure this was understood, the study group would have to analyze every moment of a hypothetical mission, on the ground, in space, on the moon, and during the return to Earth, from the time stacked vehicles were rolled toward the launch pad until the command module was recovered in the Pacific Ocean. In other words, the North American-led study concentrated on getting reliable hardware to the launch pad. The Grumman-sponsored task aimed at making sure that equipment would be able to handle the job of getting to the moon and back. The group soon realized it had to pick out an arbitrary mission launch date. They chose May 6, 1968, to give realism to the plan and to focus attention on every move, every procedure, in the minutest detail. Working out the specific position of the moon on that date in relation to the Earth, members drew up a precise launch trajectory. Then, assuming a given number of hours spent in flight and on the moon, they calculated the corrections in the return trajectory that would have to be made to accommodate changes in the Moon-Earth position. The task was not an easy one. It took 4 months of hard work to produce 3 thick volumes describing the sequence of events and related actions. The work would have to be updated later, of course, but the contractor had a better understanding after the exercise of what their subsystems should be and what they should do. Thus, long before the astronauts embarked on an actual lunar mission, the mission planners, government, and contractor had spent untold hours agonizing over every minute of that trip. The Design Reference Mission Study led neatly into the requirement for North American to accelerate Block 2 command module work. That vehicle had moved slowly following the lunar orbit mode decision. Until Grumman got the lunar module design relatively well set, North American engineers would have only the most general ideas of how the 2 vehicles would rendezvous and dock, which limited them to guesses about the influence of the docking equipment on the command module weight. The following spring, however, new mission rules gave them a clearer picture of what they were designing toward. The crews would be able to stay in their couches during docking, and the connection between the command and lunar modules would be rigid enough to maintain a pressurized pathway through which the astronauts could travel between the craft. North American engineers favored probe and drogue devices to dock the command module with the lunar module. The command module probe would slip into the lunar module's dish-shaped drogue, and 12 latches on the docking ring would engage to lock the spacecrafts together airtight. The astronauts could now remove a hatch, take out the docking devices, and travel between the 2 spacecrafts. When operations were finished, they would return to the command module, reinsert the devices, install the hatch, and release the latches to disengage from the lunar module. By mid-1963, North American engineers had begun work on an extendable probe on top of the command module that would fit into a dish-shaped drogue on the lunar module. They considered 3 possible ways of docking. First, soft docking, which meant latching and then reeling the vehicles together. Second, hard docking, which meant going straight in and latching without preliminaries. And third, transferring the crew by extravehicular means, which meant getting out of one spacecraft in free space and climbing into another vehicle. This would only be used in an emergency situation, though. Finally, it was now apparent to North American that the main difference between the Block 1 and the Block 2 spacecraft was that Block 2 would be equipped with the means for docking and the pressurized crew transfer tunnel, but Block 1 would not. By March 1964, the Manned Spacecraft Center and North American were close to agreement on the design of the Block 1 command and service modules. A mock-up review board was preparing to go to Downey with a team of systems and structural specialists to examine every part of the proposed model and decide what items to accept. Following NASA's tradition in engineering inspections, the board would consider 4 categories of changes. First, approved for change. Second, accepted for study. Third, rejected outright. And fourth, found not applicable. The review board would rule on the suggested changes on the basis of technical accuracy, desirability, and feasibility, and the impact on cost and schedules. At the end of April 1964, a 100-person group gathered at North American's Downey plant. After being welcomed by contract officials, members of the board and their specialists watched as several astronauts simulated operating the device. Next came a walk-around for a general examination of the spacecraft mock-up and such special displays as wiring, cutaway models of subsystems, parachute packing, and electrical connectors. Managers and counterpart engineers from NASA and the manufacturer then split up into small groups to examine minutely and evaluate each piece. More than 100 requests for changes were written on the spot for consideration by the board. 70 were approved, 14 were designated for further study, and 26 were rejected. The spacecraft couches worried the board members a great deal, since the crewmen, wearing pressurized suits, fitted too snugly into their seats. As a matter of fact, an astronaut lying in a couch could not move easily even in an unpressurized suit. 3 pilots lying side by side in the couch area would be virtually immobilized. By July, adjustments had been made to alleviate this situation and to cover other suggestions by the board and its assistants. After a second mock-up review in September, NASA told North American to begin production of the Block 1 Earth Orbital Command and Service modules. After Project Christmas Present and the decision to use redundant systems rather than making repairs en route to the moon, work on the Block 2 spacecraft began to move a little faster. Since 2 large vehicles, the Command and Service Module combination and the Lunar Module, would be boosted into space, a weight reduction program became of major importance. North American met this challenge principally by shaving kilograms off the command module heat shield and the service module structure. During the spring of 1964, continuing problems with the Block 1 and Block 2 vehicles triggered a change in management at North American. Dale Myers, program manager of the Hound Dog missile, took over as Apollo manager, replacing John Paulp. Myers, a company employee since 1943, later remarked, quote, "The first thing I did when I got on the program was to work out with Joe Shea a program definition phase for Block 2. We set up all the milestones we had to go through in getting to the definition of the Block 2 vehicle." End quote. Shea and Myers assigned teams at Houston and Downey to guide the definition phase of Block 2. Alan Collette led the contractor team, and Owen Maynard headed the NASA group. Both men had worked on Apollo spacecraft design as far back as the feasibility studies of 1960. Under their leadership, teams concentrated on such activities as charting and evaluating changes caused by abandoning the in-flight repair concept, finding places in the cabin for lunar sample boxes, studying the design of the pressurized tunnel that permitted astronauts to move from one vehicle to another, eyeing the probe and drogue docking mechanism, reviewing the heat shield and service module weight reduction programs, and modifying the service module design to provide an empty bay to hold scientific experiment equipment. Maynard and Collette planned to hold their Block 2 design review meeting in August, but it was September 29th before the 130 board members and specialists had something at Downey to examine. But even this was not a complete mock-up of the Block 2 command module, as some NASA officials had expected. The contractor presented mock-ups of the command module interior, including the arrangement of the upper deck and lower equipment bay, and the service module with 2 of its 4 bays exposed. Although the couches from the April Block 1 review were still featured, the harnesses had been modified to afford roomier seating. The hatches enter and out were the same as for Block 1, and the spacecraft exterior reflected only the changes from Block 1. New systems such as docking and crew transfer were sketched out in little detail. After the specialists had examined the mock-up, they submitted 106 requests for changes. The board accepted 67, recommended 23 for further study, rejected 12, and returned 4 as not applicable. What worried everyone, government and contract employees alike, was the lack of good, solid information on how this vehicle and the lunar module would work together on rendezvous and docking. Across the continent at Grumman's New York plant, however, the lunar module contractor had a mock-up that would be ready for formal review in October. That would give North American a clearer picture of exact changes necessary in its spacecraft. In 5 months after these changes had been studied and incorporated, a formal Block 2 command and service module review would be held. Meanwhile, 1 engineer from Houston and 1 from Downey would be assigned to each of the 67 requests for changes that the board considered critical. Essentially then, waiting for the lunar module to settle into its final form became a way of life for North American engineers. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.